Now, I wasn't certain of the time, so I'm going to give you a whistle-stop tour of some of the marine robotics work we're working on. Um, Currently, we're significantly funded by SFI on the Marine Renewable Energy Ireland for the operations engineering, but we've been funded by Engineers Ireland, H2020, and many other sources. So, time permitting, quick look at the team, some of our early work, what got us going, and then focus in on the ocean engineering, robotics in MRE, and then we look at remote presence, controlling robots remotely, because operating offshore in the ocean is expensive. If you have to mobilize a ship to go out there every time a Hurricane Henry or whatever blows through, it becomes prohibitive. So operating this future, marine renewable energy future we envision, every time a storm blows through, it becomes operationally very expensive. So can we do a certain amount of monitoring, inspection, repair and maintenance without mobilizing? So in some respects, there's overlap to space robots in that we are interested in a certain amount of teleoperation. I guess it's worth saying that some folks in the marine robotics world call it inner space, in that we look up the heavens, we can see to the far-flung galaxies, we can see back to large fractions of the time to the start of the universe. Stand on the prow of a ship and look into the ocean, you can hardly see 1 meter through the water. So in many ways, the seabed and the ocean environment is hidden from us. That's a quick look at some of the team. So we started making robots, AUVs and whatnot, but around the early noughties. In early noughties, we ended up teaming up with marine scientists. So that got us engineers out of the lab and trying to deal with stuff in the ocean. So that image is a regridded seabed terrain based on data captured by the Irish National Seabed Survey. Our brethren in Galway did the regridding, and when you regridded it at a lower geometry, lo and behold, certain mounds started to appear. And back in the early noughties, they discovered that the deep oceans have coral mounds. So we ended up funded by HEA PRTLI, working on investigating coral mounds. We were the engineers going out trying to put the imaging sonars, the precision navigation on robots, and they're interested in the data for investigating sonar mapping, video analysis and sampling for to map the extent of the coral mounds in the ocean. There's significant coral mounds around the edge of the national shelf, and there's some images of them just there. When on this ship, we were integrating sonar and navigation instruments on a hired-in robot from Norway, and kicking the tires, we thought to ourselves, there's not a lot in that we can't do. So that's exactly what we did. We started off building our own robot. So we are essentially an engineering technology research centre addressing challenging domains in ocean and airborne environments. This is on an auto feed, which I didn't expect. Anyway, so the smart technology, some of our systems and some of the ships we've deployed these on offshore. We've gone backwards, I'm sorry, or else I have slides repeated. No. There we go. Okay, Irish seabed territories. The oceans are vast, but the Irish seabed territories 10 times our land mass. So how do we access these? So this ROV Lattice we built is a 1,000 meter depth rated ROV, so it can access 80% of that territorial zone. The National Holland one can go to 3,000 and odd meters, so it can access the full territorial zone. So robotics in ocean energy, very widely used in offshore oil and gas. Offshore oil and gas, except in the shallowest waters, wouldn't exist without marine robotics for inspection, repair, service, maintenance, etc. Marine renewable energy, it's not operational. We don't have operational utility scale marine renewable energy, but think about it. We want to put wave devices out in the ocean. We want to put tidal energy devices out in areas of very high and strong wave and tidal energy. This isn't the location of choice for conventional ocean energy. So in fact, we're expecting an awful lot more of our robots if we want to be able to construct, inspect, repair and maintain in this challenging environments. So that's the unique challenges for ROVs and the other robots working in that environment. So what we're looking to do is our projects address significant constraints in the rollout of and expansion of marine renewables. So it's wave energy devices, tidal energy devices, offshore wind, and that offshore wind is the one that is already mature. Offshore wind is now looking at going onto floating platforms so that it can go into wider territories and deeper waters within the ocean. So we've been working in this space for, as I say, it's 16 years or so now. We've patented technology in multi-sonar control. So we've done a lot of work in underwater navigation. Navigating underwater is challenging because radio waves do not propagate through the water. So we can all navigate now because of GPS systems. Our cars can tell us if we're on the road and help us get to our destination. That is much more challenging underwater because GPS is not available. Radio signals are not available. So Rob laughs at some of the key features of this ROV we built. Maybe based on the time window, I'll not dwell too much, but it's an ROV system we've built and operated offshore on about 10 offshore surveys over the last number of years on multiple vessels. So just some images of the design, construct, fabrication, and eventual maiden voyage off the Celtic Explorer. This image, an image borrowed with permission from Siemens. The reason I like this image, the offshore is a challenging environment. If a storm blows through, such as Storm Henry, was it called there yesterday, you know, there were 30, 40 meter waves crashing off the North Donegal coast. So operating in that environment, we want our engineering structures to survive in that environment. We need to be able to inspect, repair, and maintain them in that environment. So robots and ocean energy. Conventional ROV operations in offshore oil and gas, they punch through the splash zone down to the seabed. They operate in relatively quiet water, even if the surface is maybe up to sea state 4. We want wave energy devices in the high energy splash zone or tidal energy devices in zones of very high energy. So if we want to be able to inspect, repair, and maintain, we don't want to wait for the one day a year when we get a flat calm sea. We want to be able to move up along the sea states, move along the current regimes, and perform these robot tasks. So that's our challenge. We want to move that, along the diagonal in that three-dimensional matrix. And current ROV technology can't really do that. Some of the screens of the controls. So we're effectively a control engineering group who develop control systems for getting these robots, applying semi-autonomous pilot control so that pilots aren't overwhelmed by the disturbance from the wave motion, the drag from the cable, while addressing the intervention or inspection task they're trying to perform. In wave energy devices, which are heaving up and down in waves, do we need to inspect those devices? Do we need to inspect the anchor chains which are heaving up and down in the ocean? So our target is potentially in motion. So we've developed some screens. The 2D plan view is as simple as possible. We want numbers floating with the devices. So these ship on the surface, the ROV in the plan position view, follow the actual instance, the real ship, the real ROV in the ocean, with the heading, with the depth, all that visible without the pilot having to scan from display to display. Advanced pilot interfaces. We could show you a lot of detail here, but there's a live video of some of the information captured from an ROV surveying a seawall with the sonar image inlaid up on the top left and the pilot control view on the right. So I'll skip ahead. This is another view of an ROV operation in Bantry Bay doing a survey on a wreck called the La Cerf-Volant. I can't remember French. One of the many failed sort of revolutions in Ireland. A lost wreck. Okay, Ellie Etna, and we operated on the back of the Ellie Etna, the flagship of the Irish Navy, with our ROV system doing a survey of the UC-42, a German World War I wreck, which sank itself driving back over its own mine. They expect what happened was a destroyer maybe came over the horizon. The U-boat, which was laying miles, reversed over its own mine, blew itself up and sank to the bottom. So sorry, if I can just launch that video. I should have had it launched while I was speaking. So downward-looking cameras, forward-looking cameras running over the wreck, and we won't have time to go to see the whole thing in. So more video. We'll get to the interesting part. This is the real-time capture of the sonar imagery over that wreck. Further along the same wreck, and then first look models of the U-boat on the seabed, etc. And that's it, like, if you like, a digital model of the wreck. Another wreck survey, smart controls. We're now surveying 40 miles off Bloody Foreland, 160 metre depth, a ship which is 2 meters short of the Titanic. That was the largest ship ever sunk by a U-boat, and it was sunk in the Second World War, the Empress of Britain. So we're operating in a sea state 4. We're operating with the ship into weather, with the ROV down at 100 meters, with the ship, with the target 60 meters below, and the ROV and the ship are working in tandem. With autopilot control on our ROV system, we can command the ROV and the ship. So the ship has DP, it's the Celtic Explorer, and it's crabbing along the wreck. So the wreck isn't aligned in the direction of the ship, the wreck is aligned in whichever direction it falls, and the ship has to face head to weather. So that's some first looks of the sonar imagery of that wreck. We'll skip ahead. Some of the features: operating in strong currents. We want to be able to hold the ROV on the target. So if the ROV cannot hold against the 3-4 knot flow, often surface vessels have more powerful thrust. So we can leave an ROV back onto a wreck on their surface vessel thrust, with the ROV still controlling its surge and sway and yaw, potentially. So numerous offshore surveys there. I won't dwell, I'll continue. So some of the work we're now focusing on, in order to, if we want to be able to operate an offshore marine renewable energy devices which are heaving in the ocean, how do we inspect these devices? How do we even register relative to these target devices? We don't have a fixed target device. So GPS, we have GPS when we're on the surface. We have an inertial navigation system which fuses the best we can do with sonar, acoustic position, Doppler velocity log against the seabed, GPS until you dive. But even with that, it's very difficult to get of the order of centimeter precision in control. So what we need to look at is precision control relative to the target. And the way we're trying to address that is based on image processing. So we have a heaving device in the ocean. The ocean might be turbid. There will be wave bubbles entrained in the ocean. There will be light variation with the wave motion. So we want to image the targets with cameras and sonars and fuse that imagery with the known geometry of the targets in order to extract pose of the robot and the robot manipulation relative to the targets, to aid in complete survey, 100% survey of the vehicles and intervention. Intervention is obviously more challenging. So the key to this is we need to be able to do those imaging tasks in real time. So that's exactly the focus of this imaging research that's ongoing at the moment. The other thing, if we want to be able to manipulate, the image built in there is a commercial ROV that works in offshore oil and gas. It's an oceaneering ROV. It's extending its manipulator and it's going to operate some valves. If you notice, there's a certain amount of motion, but we're in relatively quiescent subsea environment. We're way below the surface. We're way below the splash zone. Can we do similar tasks in the splash zone with Sea State 4, for example? That's going to be challenging. If we can't do it, maybe we should forget marine renewable energy. We have to be able to do this, or else marine renewable energy becomes unserviceable. So again, there's some imagery here. We're trying to develop and cross over some of the control techniques used in industrial robots. Industrial robots use precision servo control such that the industrial robot, the robot arm, knows where it is in its own reference frame. The robot arms on underwater robots are like the backhoe on a JCB. They're controlled by pilot through video in the loop, but they don't know exactly where they are. So we're looking to integrate industrial servo-controlled robotics with real-time image processing with base vehicle control. So that's the challenge. If we can wrap all that up into a real-time control package, can we interface with a moving target? And before we try to grab onto 10-ton targets, we might see if we can catch a passing fish. Less chance of breaking ourselves. Anyway, so we've been gifted by Science Foundation Ireland funding to go after a marine renewable energy ROV. So we want a high thrust weight ratio ROV that can deal with significant, sorry, how did that go off? Sea state conditions, and we want to supplement this with our advanced control systems. So remote presence. The other thing we want to be able to do is remotely control robots in the marine environment so that we don't have to mobilize a ship every time a Storm Henry blows through. So we've been involved in European projects in this space. So for example, that's a map overlaying the ship tracks around the Irish coast over a year period. We do have offshore accidents every now and again. That's the Whiddy way back when. Some Russian ship that leaked a whole bunch of fluid into the Irish Atlantic as captured by satellite. So in order to survey these zones, obviously UAV technology will allow us quickly survey. We've, in this exercise, operated a number of ships. The idea was to use robotic platforms to get as much information from the real-time environment back to command so that command can plan safe deployment of first responders in the instance of a marine incident. So the marine incident this exercise evaluated was a ship coming into Shannon Estuary, asking to come in because it had trouble, floundering, hitting a rock on the way in, losing power, taking on water, losing bunker fuel, shedding cargo off the deck as it listed. And you don't know, is it noxious and harmful cargo? You don't know. You want to map the extent of the oil slick, etc. So the idea, we need to segregate airspace for this first response, emergency response. The emergency response was led by the Coast Guard as the natural leader of the Coast Guard. We had Navy on as the lead on the water command, and our task was to feed real-time robotic feeds into the command as shown on the bottom of that slide in real time. So I'll quickly show a video, which I doubt that I'll have enough time. Command center was in Money Point. That's the site inside Money Point. So I'll skip through the video rather than let it run its full 2 minutes or however. Missing cargo. So we're searching for shed cargo on the seabed with ROV lattice. We put ROV lattice in the Shannon Estuary now. The river is flowing at 1 meter or of that order at this point in the tide. So the ROV control system has to deal with the fact that the flow is pushing it sideways. That's the forward-looking sonar imagery. And then we have UAVs as well, and AUVs. I'll skip ahead. That's it deployed again, is it? I'm sorry. Have I a double video? No, maybe there's more detail on this one. So that's the forward-looking sonar which has found that cargo. The idea is to survey that cargo. And then this is a complicated movement where we're circulating the cargo in a river, something a human pilot could not do without the aid of advanced navigation systems. So we do a clockwise and then an anti-clockwise, then a clockwise traverse around the target to image it. This is another exercise in the same thing in port exercise in a partner. Okay, so we want to be able to remotely control these devices in the ocean. So we want to add security to that remote control, so that encryption, so that nobody can interfere with our activity. So that work is ongoing. And on the next, have I got this? Maybe I have my slides slightly the wrong order. The other aspect is we have shown that we can remotely control these devices through the internet in real time from Dubai, from Italy, from North America. We want also to be able to control them offshore. So in the offshore, we will need radio communication. So the high-banded radio communications needs direct line of sight, which means beyond the horizon becomes a problem. There's now Ka-band satellite provision, which extends significantly out to sea. If we go into the deeper ocean, we have to see, can our systems be delay tolerant, real-time control systems that are delay tolerant for satellite comms. So that's also ongoing research. We want to be able to inspect offshore plants. So can we take off, inspect, and land UAV systems on remote platforms, be they ships or heaving marine renewable energy platforms. So that's UAV research. We're active in UAV research, etc. I think I'm coming to an end. That's an automated parafoil system for wind energy generation, but also for sensors aloft to extend your radio horizon and your sensor horizon offshore. I think I'm nearly there. Some of the UAV systems will not dwell. Large waves out to sea, and that's me. Thank you very much.